All right, thanks everybody for joining. And in the next upcoming 15 minutes, we will talk about SpinKube, WebAssembly, and Spin, the developer tool for building WebAssembly-based applications. My name is Thorsten. I work at Fermyon. We are Akamai QCP, and we are all in building or unlocking server-side WebAssembly and give you like different runtimes that you can either host on your own, on your Kubernetes cluster, so we are using LKE as part of this session, or that you can throw on top of Akamai's connected cloud to run them across the globe close to the edge. Let me quickly jump into my other slides. There we go. So first and foremost, so both Spin and SpinKube have been contributed to the Cloud Native Computing Foundation and are right now on the sandbox tier. So Spin is essentially the developer tool that your developers can use to build WebAssembly applications using different languages. So as of today, we support languages like Rust, like Go, TypeScript, JavaScript, Python. Zig is also in there, obviously C++, and we have experiments with C# so that you can compile your .NET workloads also to WebAssembly and run them on different runtimes. So Spin is also a runtime that developers use in the inner loop to, test their workloads and get a sense of how things work. And once you're done with building, you have to run those workloads at some place. And SpinKube is the open source runtime that you can deploy to any Kubernetes distribution and run your WebAssembly workloads next to your containerized workloads. In contrast to traditional containers, with SpinKube, we don't leverage containers as an execution mechanism. Instead, we have a different container shim implementation to spawn every application as a subprocess on one or on multiple of your worker nodes. And this allows us to run with a way higher density. So in contrast, you can basically max out your Kubernetes cluster depending on how many pods you are allowed to run on a particular node or how big your IP address range is. So those are the limits that you will face with SpinKube, in contrast to traditional containers where you may end up having a way higher resource utilization and hit those limits way earlier. So SpinKube is not something that we build on our own. It's a joint effort from folks at Microsoft, SUSE, Liquid Reply, and us at Fermyon. And as I mentioned, we contributed Spin and SpinKube to the CNCF. And I think we're right now 6 weeks in on the sandbox tier. So to dive a little bit deeper into the runtime, so you can think of SpinKube as an open source stack that you deploy to your cluster. Achieving it from the bottom to the top. So there is a container shim for Spin that is deployed to the Kubernetes nodes that you decide. So you can go with one, you can go with all, or you can go with nodes with GPUs if you have like machine learning, AI-centric workloads. And that's basically what's responsible for running your apps. We have a runtime class manager, which is essentially a node installer image that takes the container shim and deploys it onto your nodes. And we have 2 CRDs that will be deployed to your cluster. One is the Spin app that represents a workload, and the other one is the executor, which is basically like a loosely coupled mechanism to link an app to one of the executors that you may have in your cluster. So this allows you also to, have different isolation barriers like namespaces for teams or for different products that you want to run on your cluster. Last but not least, there is a plugin for the developer tool, the Spin CLI, to streamline manifest scaffolding so that you don't have to write a YAML manually in order to get your app into the cluster. All right, there are a couple of slides over here that talk or explain the developer workflow. And with Spin, we try to stick with a language agnostic workflow. So it does not matter if you're a Python developer, Rust developer, Go developer. You always follow the Spin workflow, which is Spin new to create a new project, Spin build to turn your source code down into WebAssembly. Then we have to distribute the apps somehow. And a spin app is always distributed as an OCI artifact, so you can use whatever OCI registry that's available in your organization to store your spin apps. So that's as easy as doing a spin registry push. If there's authentication required, you can do a spin registry login beforehand to ensure you're authenticated correctly and authorized to push there. As I mentioned, the Kube plugin for Spin gives you that scaffold command, which generates a bunch of YAML that you can then maybe manually apply, or if you're used to use Helm, or if you want to use GitOps, you can use those manifests with all those supported ways to get software into your Kubernetes system. Before we dive into a demo, let's have a quick look at the Spin operator. So basically it's watching the Spin app CRD, and whenever we create a new object of that CRD, we create those Kubernetes primitives that you're used to use, right? So there's underneath the Spin app, there's a deployment, there's a service, and you can configure if you want to have a service by default or not. And the deployment obviously consists of that amount of pods that you specify as replicas. In contrast to container, no container is spawned on the underlying node. Instead, a simple subprocess is spawned responsible for serving those requests. And this, gives us the freedom of running way more workloads on the same set of compute resources because there's no container overhead. And we don't have cold start times of at least 3 seconds for a container to become ready. We can get ready as fast as the network is able to pull the app and to instantiate the workload. So let's have a look at how that would look like with a new app. So, Spin, new. As you can see, we have a set of templates, and you can always create your own template. So if, for example, let's say it's pretty common in your organization to build CRUD APIs using TypeScript, you can create a custom template that brings a lot of the glue code and the plumbing so that your developers can focus on solving business requirements instead of, repeating themselves again and again and again. So let's roll with HTTP Rust for the sake of this one, and let's say hello-LKE. And depending on the template, you may ask different questions. So this one is triggered by an incoming HTTP request. That's why there was a question of, hey, on which paths should I respond to? If you trigger based on a message queue, you may have to specify an address, a channel, and so on and so forth. Okay, if we cd into that directory over here and open it in VS Code, you see this should be big enough. Depending on the language of choice, this looks super familiar, right? In JavaScript, that's an idiomatic JavaScript or TypeScript project. And the same is true for Rust. So this is a pretty standard Rust crate. Although there's one exception, there is the spin toml file, which is the application manifest. And that's where we, for example, bridge those language agnostic commands like spin build down to what is required to turn Rust code in that example into a WebAssembly module. And one of the key value propositions of WebAssembly is that it is strictly isolated and secure by default. Meaning we as developers, we have to explicitly grant permissions to our workloads in order to give them access to external resources. Like, for example, if I want to call out to the GitHub API, that would be https://api.github.com, right? So I have to explicitly mention that. That's what the Spin manifest is all about. At some point, I start implementing my application, right? So this is a super simple HTTP response returning hello world. Let's change that to hello LKE. So it's responding with an HTTP 200 and returning a simple payload and an HTTP header. Once I'm done with implementing my app, I take the next step in the Spin workflow. And this is basically a Spin build. So that downloads all the dependencies and turns my Rust source code into a WebAssembly component. Okay, the compilers are right now yelling at me because I did not use that request argument, but it's fine. Next is I want to try it locally, right? So I can do a spin up over here, and spin takes care of creating a listener and routing requests to my WebAssembly workload, which is a cold start for every request that hits that endpoint. So let's split the terminal and let's try the app, curl localhost 3000, and we see we get super hello LKE back over there. Okay, so now I am confident that my app works. I want to deploy it on top of LKE. So I created a simple LKE cluster and deployed SpinKube already on top of it. And within the default namespace, I have one of those CRs, a spin app executor that tells the cluster, hey, whenever someone gives you a spin app with an executor named containerd shim for spin, then use the containerd shim for spin instead of spawning a container for that particular workload. Okay, so I can do, I now have built my app, I ran it locally, I know that my cluster is ready to go, I have to distribute my app, right? So that is a spin registry push. I'm right now using TTL-SH, an ephemeral registry where I can store my images and the tag defines how long they will be available. All right, we got confirmation that our app is distributed to TTL-SH. So now I have to create those Kubernetes manifests, right? And that's as easy as doing a SpinKube scaffold. But instead of directly piping it to kubectl, let's have a look at what we got, right? So let's do it again. So we get a simple manifest indicating, hey, this is the OCI artifact I want to leverage. The link to the executor, right, to instruct Kubernetes, hey, spawn this app instead of a container. And it mentions 2 replicas. However, we can do more. So the SpinKube scaffold command has a vast amount of flags that you can use to bring in support for horizontal autoscaler, for CADA, or to manually define how many resource limits should be assigned to that workload, and so on and so forth. At some point, I made my way through that and say, okay, now I'm ready to deploy the app. And it's Kubernetes basically confirming, yep, I got your app, so we can do a k-get spin app. And we see we have already 2 instances ready and 2 are desired, so we can double check, get pods. You see, I have a hey pod running there, that's a traditional container, but we have those 2 hello LKE apps. Okay. So let's do one thing right now. Let's kubectl exec into hey. And I can now say hey for, let's say, 5 seconds, call into hello LKE. So I'm basically making a load test for 5 seconds on the service sitting in front of those 2 replicas. And after 5 seconds, we should get the response back. And as you can see, we were able to process 71,638 requests within 5 seconds with the average, where's the latency distribution over there? So 99% of those requests were processed in 7.7 milliseconds or less. So now we can take that one step further if we do, let's do a k-edit spin app. And let's go all the way up, let's say to 20. And because those WebAssembly distributables are so tiny in size and so easy to start up, we are already up to 17, okay? So within a couple of seconds, we are up to 20 instances horizontally scaled. And if we do the load test now once again for 5 seconds, we should end up roughly about 130,000 requests per second. No, entirely, yep, total data requests per second. So roughly 25,000 requests per second. And all this is a single node LKE cluster, small size, I think 8 gigs of RAM, 2 CPUs. So that's fairly impressive, and you can obviously scale as, you know, the number as high as you allow, as pods are allowed on that particular node, or as many IP addresses you have. But one of one additional advantage of WebAssembly is its portability, right? So you can change the underlying operating system, the underlying architecture, without you having to recompile, right? WebAssembly is portable across those architectures and across different runtimes. So a week ago, the two of us, so Fermyon and Akamai, we announced a new thing, and we said, hey, we can take this incredible fast compute and put it on top of Akamai's cloud, where we have incredible fast network. And this is what we call Fermyon Wasm functions that you can easily run your workloads on top of. That's a multi-tenant service that we provide that nicely integrates with your Akamai property, for example. And getting there is as easy as doing in the same folder a spin aka deploy, which takes the app, takes that artifact, pushes that up into the Fermyon Wasm functions registry, and now we distribute the app globally across the Akamai network and make it available for all the regions. And we have ALBs in front to route the request close to where your users are. So it takes roughly about a minute to ensure that the app is distributed across all the regions. And yep, we should be up and running in a minute, which makes me overrun for exactly 1 minute. So bear with me for that. Yeah, there we are. We got a domain name assigned. And if we right now check, so if we right now do a curl with oh, come on, I did not copy it. There we go. So if we curl it, we can see that this request is handled by the deployment in France, Paris, indicated by this cookie value, and that the end-to-end execution time within the Akamai platform took 2 milliseconds, right? And with that, thanks for your attention. If you have further questions, talk to us over here at the Akamai booth. We're happy to answer. Thank you.